Alright, so this is an introduction to the general solution using the equation method, not the quadrant method. So before we go on to the general solution, I need to explain what the whole point of it is. So here's a sine graph. The red graph is y equals sine x, and then the blue line going straight through here is working with y equals to a half. So just to see it a little bit better. So the idea is, the question would be, where would sine x equal to a half? It's from earlier grades, you would just use your calculator, shift sine of a half, and get the answer of 30 degrees. But that's just one point, and that's this point right over here. Alright, so that is just one point. That's the first acute angle that you'll find, where that blue line crosses the red curve of the sine graph. So we need to find the rest of them. Now, if we're having a look, we can see that the blue line is going to cut on just this graph from negative 360 to 360 4 times. So how do we find those 4 values? And also, realistically speaking, we know that this curve is not just from negative 360 to 360, it's infinite. And so we can keep going from negative infinity to positive infinity. There's going to be an infinite amount of answers where this blue line is going to cross our sine curve. So where sine x is going to curve up and equal to a half on a graph. So when we're working with the general solution, it's like in number patterns where we have a general term. We don't necessarily want to figure out an entire number pattern. So we make a general term, a rule for the pattern, and then we apply that whenever we need to. We then use it when we need to know the 6,000th term, when we need to know which term equals 25. So when we're working with the general solution, it's the same thing. We want to make like a general term, a rule, a formula that we can use to find any time in the sine graph's existence from negative infinity to positive infinity where it crosses the line y is equal to a half. So in order to do that, we look at the sine's period of the graph. So we'll go from this 30 degrees, that our calculator helps us find that. And then we know that it's going to be every 360 degrees, a repeat in the pattern. That is sine's pattern, its graph. So the next time we're going to see that same point, we call it a point in phase, is 360 degrees later. So that will be at 390 degrees. So now the thing with sine is that it has an upslope and a downslope, which has 2 different values. So when we're working with the up part, you're just going to take your acute angle and add 360. So when we're working with the downslope over here, we're also going to hop 360 degrees either way to either an upslope or a downslope. But in this case, if we're going downslope to downslope, it's the green. Upslope to upslope, we'll be working forward or backward, working with the yellow. From 30 degrees plus 360 degrees, or the green plus 360 degrees. So now what's the green? The green links to 180. It's 180 minus your 30 degrees, which is 150 degrees. And then either we add 360 to get to the next downslope, or we subtract 360 to get to the next downslope on the other side. So we're working with the yellow is the angle that we were given, the acute angle, plus every 360 degrees forward or backwards. And then your green is 180 minus the angle, the acute angle, in this case 30, plus every 360 degrees. Alright, so when we're working with it, sine, you take for your angle, in this case it's x, sometimes it's theta, alpha, beta. You would take your given ratio, in this case it's a half, shift sine on your calculator to get your inverse, and then you're going to work with plus k 360, and then 180 minus the angle your calculator gives you, plus k 360. And it's 360 because of the period of sine, and its k is an integer because that's talking about your hops. So it's 30 degrees, I can hop 1, so that's k is 1. Then I can hop 2, I can hop 3. So if we want to know where another one is in however many hops, we could say x is equal to 30 degrees plus, let's say, 6 lots of 360, just like your general term. So that would mean that we've hopped 6 times to get to another upslope. And so then you would work with 30 plus your 6 times 360, which would get you 2,190, and that would be another upslope in 6 hops time. So you can work out between certain intervals. Here's negative 360 to 360. It could be from 0 to 5,000. What are the values where that crossover is going to happen between the sine graph and the line y equals a half? Now for cos, it's the same idea, but cos is a little less complicated because the crossover will happen for cos at, in this case, 60 degrees for, if we say shift cos of a half, and then here this will be negative 60. And then we work with downslope to downslope. We'd be adding 360, and then downslope to this downslope we would subtract 360. So that would happen at 300 over there. This would then happen at 420. And then from this upslope to the next upslope, we'd add 360, and then this one to the next upslope, we'd subtract 360. Right, so that'll be negative 420. So in this case, that's going to be, this one over here is 300. So we have negative 60, positive 60, 300, negative 300, 420, negative 420. So it's the same, but positive and negative. So cos's rule is easy. We say our x value will be plus minus whatever we get on our calculator when we use shift cos, and then every 360 degrees. So you can write it as 360k or as k 360. It makes no difference. K is an integer, so we hop in positive and negative numbers, no decimals. Tan is the easiest because it doesn't have a change in direction. So once we work out what that first acute angle is, which in this case is 26,57 degrees, tan will go every 180 degrees. So you add 180 or you subtract 180. So tan's rule is going to be tan negative 1 of whatever ratio they've given you. In this case it's a half, plus k 180 degrees. K is still an integer. Right, just like when we're working with our general term for number patterns, but in number patterns is not an integer, it's a natural number because you can't go backwards into negatives. But because we're working with a graph with degrees here, we can go into the negative section. Alright, so here's an example where we're going to work with the general solution as well as restrict it to a certain interval. So normally you won't be given a graph for this, but I've put the graph in so that you can see that our answers do match up. So in this case it says solve for beta, where beta is between negative 180 and 360. Solving means solution, general solution. So you always do the general and then you find specific for the interval. So in this case I've got cos beta is equal to 0,2. So just like in the examples before, I'm saying this means where does my cos graph equal to 0,2. So in this interval, you can see it's going to happen 3 times because this is negative 180 to 360. But we've got to find those 3 times, and we've got to do it as if we don't have a diagram. So as soon as you have sine, cos, or tan angle equal to a number, that's the point when you can say shift on your calculator. So if I say shift in my calculator, cos of 0,2, your calculator will show you something like this. And then you can click equals, and it's going to tell you that beta is equal to 78,4630, but we're going to keep 2 decimal places here. And when we're working with this, that is just that first point. But we know now that there's more things involved. So for the general for cos, we always say plus minus. So the second you click shift on your calculator, your brain must tell you to apply the general solution straight away. K is an element of integers. So now we have done our general solution. For cos, it's plus minus, because if this is 78,46, this will be negative 78,46. And then we need to see this is an upslope, so we've got to match it to another upslope. So again, you won't always have the picture, so that's why we form the general solution. So now in your calculators, you can work with the specifics. So your calculator will already have, or you can type in just the 78,46. Add 360 degrees to it in your calculator, and that gets you 438,46. That falls out of our interval. It does not work. So then you're going to take 78,46 and you're going to subtract 360 from it, and that's going to get you negative 281,54. Falls out of our restriction. We have to stop at negative 180. So then think about just 78,46 plus no lots of 360. That just gets us 78,46. So that one works. We can see in the picture here that it does fit in between negative 180 and 360 where the graphs cross over. Right, so then you try the negative 78,46, because you know it's plus minus. Add 360 degrees to negative 78,46, and then you're going to see that you are going to still fit within the given interval of negative 180 to positive 360, and it gets you 281,54, which happens to be the same over there. So already, if I take negative 78,46 and I subtract a 360, we know we're going to get to that negative 438. It's got to be the same thing, negative and positive. So then we also know that negative 78,46 will work. So you work with no hops, one hop of 360 forwards, one hop of 360 backwards, and then if you have to go again, you would add 720 in total, or subtract 720 for 2 hops, 3 hops, 4 hops, etc. So what's the point of this question? Your actual working out will just be cos beta equals 0,2. So beta equals plus minus 78,46 plus K360. K is an element of integers. That you're getting a mark for already. And then you say, therefore, beta for this situation must equal positive negative 78,46 as well as 281,54 degrees. So you end up getting extra marks for the specific answers. How do I know I need to give a specific answer? Because the question had the specific interval given to you. So it wants not just the general, you've got to do the general first and then the specific afterwards. Alright, so then now you can follow on the next video, which will go on to part 3 of the grade 12 trig questions, where I will cover the co-ratios, the weird identity ones, all of those that mix in with the general solution. General solution is almost a mix of all of your trigonometry that you have learned up to now. Double angles, compound angles, co-ratios, reductions, all of that can be thrown into it. Your aim is to get cos, sine, tan equal to a number, and then you can work with your shift cos and then apply the general solution. So the general solution is actually the very easy bit. It's getting to that can be a bit tricky. All right.